The first thing that we're going to talk about today is instantaneous and average power. So let's consider that I have a linear network. Okay? Like so, doesn't particularly matter what components make up this network, just that they are indeed linear. So it's some kind of resistances, capacitances, and inductances. And let's say that this network is sinusoidally excited. Doesn't particularly matter if I'm exciting it with a sinusoidal voltage source or a sinusoidal current source. And what I'm interested in is the voltage drop as a function of time across the terminals of this network, and the current flowing into this network also as a function of time. So I want you to notice that I've drawn V and I in such a way that our network is assumed to be absorbing power. Transversely, this is the same thing as our source supplying power, okay? So if this is a sinusoidally excited system, then we should see that our voltage V of t will be of the form Vm cosine omega t plus some phase angle theta v, which would have a phasor representation of V is equal to Vm angle theta v, and our current I of t would be of the form Im cosine omega t plus theta I, which would also have a phasor representation, in this case given by Im angle theta I. So instantaneous power is simply the power that is being absorbed by our network at any particular instant in time, okay? So it is inherently going to be a time domain quantity, because we'll see that our instantaneous power varies as a function of time. However, in order to calculate it, we are going to be able to use those phasor quantities, specifically the magnitude of the voltage, the magnitude of the current, the phase angle of the voltage, and the phase angle of the current, okay? So let's get into a little bit of math here. So we're going to say that our instantaneous power, P of t, is simply going to be the product of our instantaneous voltage V multiplied by our instantaneous current I, okay? So power is equal to current times voltage, nothing particularly mind-blowing there, right? What I'm going to do now is I'm going to substitute in our sinusoidal expressions for voltage and current here. So this is going to look like Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I, okay? Now I'm about to use a trig identity here to expand this out, so I probably need to let you guys know what that trig identity is. So I'm going to put it up here in blue. And the trig identity that I'm about to use is simply that the cosine of some angle 1 times the cosine of some angle 2 is equal to 1/2 of cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2, where this whole thing right here is going to be my angle 1, And this whole thing right here is going to be my angle 2. So if I apply this trig identity, what I'll wind up getting is the following relationship. I will have 1/2 Vm times Im cosine theta v minus theta I plus 1/2 Vm times Im cosine twice omega t plus theta v plus theta I. So I want us to observe a couple of things here with this expression. Okay. So it's broken down into 2 distinct parts because of the application of that trig identity. So first thing that I want you guys to notice is that the quantities that we would plug into this equation, Vm, Im, theta v, and theta I, come directly from our phasor or frequency domain circuit analysis. So we still don't do any analysis whatsoever in the time domain because that makes the math terrible and gross. All of our circuit analysis is going to happen in the frequency domain. And then we just take the parts of the phasors that we need and plug them in where they are applicable into this expression. So this is one of the first places in this whole class where it's literally just plug and chug, put it into the equation, and you're off to the races. All of the circuit analysis behind this has already been handled, okay? So let me ask you guys a question. Is Vm a constant? Yeah, it's just the magnitude of whatever voltage we have representing the peak value of that sinusoid, okay? So by the same argument, Im is also a constant. What about our phase angles? Are theta v and theta I constants? They should be, yeah. So effectively, this first term here is 1/2 times a constant times the cosine of the difference of angles, where those angles are constants as well. So this whole first term is just a constant value. So this represents a DC contribution to our instantaneous power, okay? And I'm going to throw something up on Desmos here in a couple of moments since I can't draw to save my life. And we'll take a look at some things. The second part over here, obviously the Vm is a constant, the Im is a constant, theta v and theta I are both constants, but we do have some time dependency. But I want you guys to notice that instead of oscillating at omega, this particular portion of our instantaneous power actually oscillates at twice omega. So we see that our instantaneous power changes at twice the rate of either our current or our voltage, okay? So this is going to be a twice omega AC term. Okay. So I want to look at what this instantaneous power might look like if we were to plot it out. And to help my lack of artistic abilities, like I said, we'll use Desmos here. So somebody give me a magnitude for my voltage, nothing too wild or crazy. 2 volts, okay? Let's make it cosine. So let's make our angular frequency, because it's not going to be anything too crazy here, 4. And then let's make our phase angle. Somebody pick a phase angle. 6 degrees, okay? So 6 times pi over 180. So this is our voltage waveform. Now let's define something for a current. So somebody give me a current. Let's do not 2 because that's the same magnitude as the previous one.
8.
I'm going to do 5 because I want it to all be able to fit on this graph without messing with the things too much. And I'm going to choose the phase angle here, and I'm going to say that this is 123 degrees. So my red curve represents my voltage, my blue curve represents my current, and now I'm going to do one last curve here, and this is simply going to be V multiplied by I, which means it represents our complex power, excuse me, not our complex power, our instantaneous power. Looks like I'm going to need to change my settings here just a smidge. So let me extend the, or actually let me confine the range on my x-axis here. So let's look at stuff from just, let's say, -1 to +5 or so. And then for our y-axis, let's make the minimum value -10 and the positive value to be, looks like +6 would encapsulate everything. Okay, so I know that this graph is really busy right now because we have 3 signals on it, but I want to point out a couple of things. So I'm going to turn off this power thing right here, okay? So the first of which, and this should be intuitively obvious, our voltage signal is just a simple sinusoid, meaning that it is oscillating between its maximum value of 2 and its minimum value of -2 over and over and over again at a angular frequency of 4 radians per second, because that's what I decided omega was going to be for this example, okay? So what is the average value of our voltage? Say it louder. 0, because we have a sinusoid. So exactly half of the time it's above the horizontal axis and exactly half of the time it's below the horizontal axis. And we could say the exact same thing for our current, right? Our current is just oscillating between +5 and -5 amperes, and it has an average value of 0 as well. So what is interesting, or at least I find it really interesting, is that most of us would probably think that our average power should be just the average currents times the average voltage. But if we did that, we would get an average power of 0 in every sinusoidal system. And that can't be true, because if it were true, we literally couldn't turn the lights on or anything like that. If on average, I plug a lamp into this receptacle and it absorbs 0 power, then I shouldn't see any light, right? And that would be true for any load. So if we look at our instantaneous power here, and I'm going to turn off the current signal and the voltage signal because it's a little distracting, we can see that the average value of this power is going to be something that is, looks like it's going to be a negative quantity based on the phase angles that we happened to choose here, right? So I'm oscillating between some peak value on the positive side and some peak value on the negative side, but now this waveform isn't centered around 0. Instead, it's actually centered around that DC term, okay? So that DC term in our expression here is actually just the average power in our system. So let me go back to that graph real quick here. So in this case, and I hope you can all agree with me, that we see that our average power is going to be some negative quantity, right? We could figure out what it is with a quick back of the envelope calculation here. So our positive peak value is relatively close to 3. Our negative peak value is relatively close to -7. So that means that we have an overall span of about 10. So I think our average power in this particular case would be somewhere in the ballpark of -2 watts. Just eyeballing this graph. Obviously, it's going to be off a little bit, but I think it'll be just below -2 watts. So what does it mean in this particular case that our average power is negative? Exactly right. So since we calculated everything from an absorbed power perspective, since our average power is negative, that means that on average, our load is actually supplying power to our source, okay? So anytime that we see the value of the instantaneous power being positive here, that means our load is absorbing some amount of positive power. Anytime it's below the horizontal axis or negative, that means our load is actually supplying power, okay? So it's sending power back to the source. This is going to happen anytime we have any energy storage elements like capacitors or inductors in our system, okay? So anytime we have temporary energy storage, we are going to see that for certain intervals of time, our load actually winds up supplying power back towards our source. And that happens on a small scale in our homes. It happens on a much larger scale with the utility grid and all of that kind of stuff too. We'll talk about the inefficiencies and stuff related to that in class on Friday when we talk about power factor and how to correct that, okay? So we've got, in my opinion, a very interesting system going on here. Based entirely on the graph and our understanding of sinusoids, we can kind of infer what our average power is going to be. We have our AC portion here oscillating at twice the frequency of either the voltage or the current. So let's go back and look at some math again real quick. Okay. So this expression, and I'm going to put a box around it. Let me just write P of T over here. And for what it's worth, you do not need to memorize this. This will be given to you on the equation sheet for exam 3. And if you were not aware, you get an equation sheet for exam 3. Is the generic representation for instantaneous power, okay? So we can always use this particular equation for any sinusoidal system to calculate the instantaneous power for any network. And then whatever the DC part of this instantaneous power calculation is, will always be our average power for that network, okay? So to use this particular equation requires us to know both the voltage drop across our network as a phasor and the current flowing through our network as a phasor. However, it may be beneficial in some instances for us to not have to find that much information. So what I'm going to do now is I'm going to very quickly go through this instantaneous power relationship specifically for resistors, capacitors, and inductors, and see if we can place it in or put those expressions in terms of either only voltage related quantities or only current related quantities, because that might make it easier to solve for these things because we don't need to know as much information, okay? So for a resistor, we know the following pieces of information, okay? We know that the magnitude of the voltage drop across the resistor is going to be equal to the magnitude of the current multiplied by the resistance. And we also know that the phase angle of the voltage is equal to the phase angle of the current. We used these relationships the other day when we were talking about impedance, but they come from just our frequency domain relationships for current and voltage for our circuit elements, okay? So using these known relationships, we could say that the instantaneous power absorbed by a resistor as a function of time is actually just going to be a factor of, so let's see, 1/2, and then let's put everything in terms of voltage first, okay? So my VM term is literally just going to be my VM term. IM could be expressed as VM over R, so that gives me VM times VM over R, or simply VM squared over R. That should look kind of familiar. In a DC system, the power absorbed by a resistor was just V squared over R, so it's effectively the same thing there. Then I'm going to have that cosine theta V minus theta I. Well, if theta V and theta I are equal, then I'm just doing the cosine of 0. Well, what's the cosine of 0? 1. So that first term right there, just 1/2 VM squared over R, is our average power. Okay? So I'm going to multiply this guy by a factor of 1 plus, because I have that same 1/2 VM IM term over there. And now I'm going to do the AC term. So that's going to look like cosine twice omega t. And since theta V and theta I are equal, when I add those two guys together, I can just call that twice theta V, like so. So that's our expression for the average, or excuse me, the instantaneous power absorbed by a resistor only in terms of the resistor value itself, as well as the phasor voltage across the resistor. And then from this, we can easily see that our average power is simply 1/2, VM squared over R. Following a similar treatment, what we'll find is that the average power absorbed by a resistor in terms of the current comes out to be 1/2 IM squared times R multiplied by 1 plus cosine twice omega t plus twice theta I. And in this case, we would say then that our average power in terms of current is 1/2 IM squared times R. So before we move on to inductors and capacitors, I want to effectively throw these relationships into Desmos really quickly and kind of see what things look like here. So what I'm going to do is I'm going to change one thing. I'm just going to make our phase angles equal to each other, right? Because we know that for a resistor, theta V and theta I are the same thing. So if I change this 123 to 6, let me change my settings real quick, make it go from plus and minus 10. Actually, let me bump this up to positive 12, just so that we can see it a little bit better. So what we can observe by looking at this graph is that the average power, excuse me, the instantaneous power, sorry for making that mistake again, the instantaneous power absorbed by our resistor is always positive. So what does that mean? Resistors only absorb average power, which is something that we've actually talked about way back on our very third class meeting when I mentioned that a resistor is incapable of storing energy. All it can do is convert electrical energy into heat. And this instantaneous power relationship reinforces that, right? We never see a negative value for our instantaneous power. So our resistor is never supplying power back into our system because it literally can't do it, okay? So another thing that we should be able to infer from this, and we kind of see it in the mathematical relationships as well. So whatever the peak value of our instantaneous power is, exactly half of that is our average power, right? Because we're oscillating between 0 and that peak value. So on average, and we're sinusoidally oscillating between 0 and that peak value. So on average, the value of this expression is just half of the peak. All right. So now let's look at our inductor relationships. So in an inductor, we know that Vm is equal to omega L times Im, and we know that theta V is equal to theta I plus 90 degrees. So when we did our lab on Friday, you guys should have found that the current was lagging the voltage by something very close to 90 degrees. It wouldn't be exactly 90 degrees for a couple of reasons. One, the resolution on these oscilloscopes is kind of shitty. But the other reason is that the inductors that we used are not pure inductors because it's impossible to generate a pure inductance that has no resistance whatsoever because we know that real wire has some amount of resistance, right? So we should have got a number pretty darn close to 90 degrees, but it wouldn't have been exactly 90. Here we're talking about pure ideal inductance, okay? So if I use these relationships, what I'll see is that in terms of voltage, I'm going to get 1/2 Vm squared over omega L, right? So I can say that Im is just Vm over omega L, multiply that by another Vm, and we get that result. Now, what's going to happen when I do cosine of theta V minus theta I? Well, so theta V is just theta V. Theta I could be written as theta V minus 90 degrees. So theta V minus theta I actually comes out to be the cosine of positive 90 degrees. What's the cosine of positive 90 degrees? 0. So that tells us that on average, an inductor does not absorb any average power, okay? Or the average power is 0. So exactly half of the time in a sinusoidally excited system, our inductor is absorbing energy, and exactly half of the time, that inductor is then sending that energy back towards the source. So it's just a cyclical thing where it takes in energy and gives it back over and over and over again, okay? So in some ways, this can represent an inefficiency in the system, which again, we'll discuss on Friday, but this very much goes along with the idea of it being a form of temporary energy storage, right? It holds on to energy until we change the current and then it sends it back out. So if I keep on going here, I have 0 for my average power. So I'll move on to the AC portion. So that'll be cosine twice omega t plus twice theta v minus 90 degrees. In terms of current, this is going to look like 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. And our average power is 0. So I want to look at, like take a quick peek at this power in the time domain. Once again, just using those Desmos graphs, where really the only thing I'm going to change this time is once again the phase angle. And for this case, I'm just going to make sure that the current phase angle is 90 degrees more negative than the voltage phase angle, so that we have a current that's lagging by 90 degrees. So I believe, actually, I'm just going to be lazy and do it this way. So putting just 6 minus 90 there to force this current phase angle to lag by 90 degrees, we can very easily see exactly what I mentioned a moment ago. Exactly half of the time, our inductor is absorbing power, which is represented by all of the positive values for our instantaneous power. And exactly half of the time, our inductor is supplying power, or just sending that energy straight back to the source. All right, so now let's talk about capacitors. So in a capacitor, we're going to have the exact same relationships as an inductor, except that we're just going to swap I and V and replace L with C. So that's going to look like IM is equal to omega C times VM. And then we'll have theta I is equal to theta V plus 90 degrees. So how this works out is we'll have PC of T is going to be 1/2 VM squared times omega C times the cosine of negative 90 degrees. Well, the cosine of negative 90 degrees is also 0. So we'll see that we have no average power absorbed by our capacitors. Moving on to the AC portion, we're just going to have cosine of twice omega t plus twice theta v plus 90 degrees. And then in terms of current, we'll have 1/2 Im squared over omega c times the cosine of twice omega t plus twice theta I minus 90 degrees. And once again, our average power is simply going to be 0. So I could show you this relationship on Desmos as well, but realistically, it's just going to look like the exact same graph, except that it's going to be shifted to the right a little bit. So these are our instantaneous power relationships for a pure resistor, a pure inductor, or a pure capacitor, expressed only in terms of either voltage and current. So one thing that I want you to notice here, some of you might have already caught on, essentially what we've got in each case is V squared over the magnitude of the impedance, or I squared times the magnitude of the impedance as our constant term on the outside, right? Because we know that the magnitude of the impedance of a resistor is just the resistor value itself. The magnitude of the impedance of an inductor is omega L, and the magnitude of the impedance of a capacitor is 1 over omega C. So in every single one of these cases, this is just V squared over the magnitude of the impedance we're interested in, and then we get into the angle relationships and all of that kind of good stuff. Let's see. So I want to work a portion of one of your in-class assignment problems here. So I'm going to open up the ICA file. If I can get to the right class. This is ICA number 22, I believe. And we're going to jump ahead actually to problem 2. I'm working this problem out with you guys, or at least a portion of this problem out with you guys for 2 reasons. One, I want to show you how to apply the equations that we just developed. 2, I want to make sure you understand a couple of nuances about it. And 3, there is a homework problem that is almost exactly this same thing, but with different numbers, that you guys asked me a ton of questions about. And so I'm trying to cut those questions off at the pass by just showing you how to do this damn thing. Okay. So we are given a circuit essentially in a written statement here. We have 3 circuit elements that are connected in parallel. We have a current source, a resistor, and an inductor. So I'm going to choose to draw that system, right? So here's my current source. Here is my resistor. And here is my inductor. Okay. Now we are going to do all of our circuit analysis in the frequency domain. So I want to represent my current source as a phasor current. So how am I going to take that 100 cosine 2 times 10 to the 5t milliamps and express it in a phasor form? So our phase angle is 0, so we're going to have an angle of 0. So 2 times 10 to the 5th is omega. Our phasor should not have an omega in it at all. It should just be the magnitude and the phase angle. So what's the magnitude here? 100 milliamps, which I'm going to actually choose to write as 0.1 amps. I'm going to put it in base units. Okay. So this is going to look like 0.1 angle 0 degrees amps, which is the same thing as 100 angle 0 degrees milliamps. But again, I want to do things in base units here. Okay. What is the impedance of our resistor going to be? Just 1 kilo ohm, because the impedance of a resistor is the resistor value itself. So I'm going to put 1 kilo ohm here. And then what is the impedance of our inductor going to be? Well, we have to do a little bit of math for this guy. So the impedance of an inductor is J omega L. So that's going to be J times 2 times 10 to the 5. L is 15 times 10 to the minus 3. And so 10 to the 5 times 10 to the minus 3 is 10 to the 2. So that's 30 times 100 is J 3000. So this will be a J 3 kilo ohm impedance. Are we all okay with that? All right. So we are asked to calculate the instantaneous power absorbed by each of these circuit elements at a specific instant in time, and that is t is equal to 10 microseconds. So I'm only going to work one of these with you guys. So you can choose as to whether it's going to be the current source, the resistor, or the inductor. So Cody, I'm going to let you make that decision. No pressure. Inductor. Okay. So in order for us to find the power absorbed by the inductor, we either need to know the phasor voltage drop across the inductor or the phasor current flowing through the inductor. I'm going to make that decision for you guys. I'm going to choose to find the phasor voltage drop across the inductor. I'm going to call this V. The reason why I'm choosing specifically to find the voltage here, even though we could find the current pretty darn easily by just using current division, is I can also use that same voltage to find the power absorbed by my resistor. And that's the missing piece of information to find the power absorbed by my source as well. So I can use this voltage as to find all 3 quantities. So I don't have to do any extra work for the remainder of the problem. Okay. So that's why I'm choosing to find V here specifically. So Now I'll ask you guys what I hope is a simple question. How might I find that voltage V for this particular circuit? I'm just not Carter. All of your impedances and then multiply it by current. Yeah, so I times ZEQ, which was what you were getting towards, except you accidentally said divide instead of multiply. Ohm's law is still Ohm's law. So V is equal to IR in DC circuits, so V is equal to IZ in these AC circuits, okay? So we would have 0.1 angle 0. And then up here, I'm going to have 1 kilo ohm times J 3 kilo ohms over 1 kilo ohm plus J 3 kilo ohms. And I'm going to take a moment to put that into my calculator. So what I just got was 94.868 with an angle of 18.435 degrees volts. Can anybody corroborate that result? Okay. So now I can literally just plug stuff into my equation. I don't have to do any extra work here, okay? So if we're finding the instantaneous power absorbed by an inductor, I'm just going to write that expression down over here so that you're reminded of it. So PL of T in general is going to be 1/2 times the magnitude of my voltage squared divided by omega L multiplied by cosine of twice omega T plus twice theta V minus 90 degrees. And now I'm going to explicitly write out how I'm going to plug this into my calculator effectively, okay? So there's my 1/2. So what's VM in this case? 94.868 volts. So one of the most common mistakes that I see students make when performing this calculation is that they accidentally put in the full phasor there. No, you're specifically asked to put in just the magnitude of your phasor voltage, okay? So that's why we're doing just 94.868, not 94.868 with an angle of 18.435 degrees. We only want the magnitude here. What's omega L? 3 kilo ohms, right? The impedance of an inductor is J omega L. Our inductor's impedance is J 3 kilo ohms. So it seems to me like omega L is equal to 3 kilo ohms. We could absolutely calculate that out again if we were so inclined, but we already did it once, so why bother doing it again? So this is getting back to what I was saying about it's literally just the magnitude of the impedance we're interested in. So I'm going to put 3 kilo ohms down here in the denominator. Okay. Then I'm going to have cosine. I'm going to put braces right here. So we should have twice omega. Omega is given to be 2 times 10 to the 5. So I'm just going to do 4 times 10 to the 5. Okay. And I'm going to make a note here to put this written down as in radians per second, because omega is always expressed in radians per second. We are asked to find our instantaneous power at t is equal to 10 microseconds. So I'm going to put in 10 times 10 to the minus 6 seconds. Okay. So when I multiply omega times t, I'm going to get an angle in radians. Well, my phase angle that's going to come up next is very obviously expressed in degrees. Okay. So I need to make a decision as to whether I want to convert omega t into an angle in degrees, or if I want to convert my phase angle into an angle in radians. Since my calculator is in degree mode 99% of the time, I'm going to choose to convert this angle in radians right here into degrees by multiplying by a scaling factor of 180 degrees over pi, okay? This is the second most common mistake I see students make, is forgetting that you can totally put an angle in radians and an angle in degrees into your calculator at the same time. And if you're not paying attention to your units, your calculator certainly isn't, okay? So you need to put this factor in here if your calculator is in degree mode. If your calculator is in radians mode, you would actually use the inverse of this scaling factor on the phase angle itself, okay? So now we'll have twice 18.435 degrees, and then I'll do minus 90 degrees, and I'll close this guy off, okay? So I'm going to break this calculation down into a couple of smaller parts because it's very easy to accidentally fat finger a number or something like that here. And also, I let everybody borrow all my good TIs, so I'm left with just Casios at this point. And I know for sure that the Casios have less memory than the TIs, and I just don't want to get random math errors or stack errors all the damn time. So I'm going to start by just doing this first part right here, okay? So 1/2 times the magnitude of my voltage. So squared divided by 3,000. Plug that in, and I'm using stored values so that I don't get any rounding error. That part literally just comes out to be 3/2. Okay. And the units for that part, so we have volt squared, essentially per ohm, is going to be a watt. Yes, Brielle. So omega L is just that guy, because the impedance of an inductor is just j omega L. So 2.5, there's going to be 2 times 10 to the 5 times 15 times 10 to the minus 3, which we found to be 3 kilo ohms, is just omega L. Okay. So I have 3.5 there out in front. And now I'm going to do this angle shenanigans here. So let me see. I'm going to have 4 times 10 to the 5 multiplied by 10 times 10 to the minus 6, multiplying that by 180 over pi plus twice the angle of what I have stored in my calculator as A, minus 90 degrees. And so to me, that came out to be 176.053 degrees. And so the cosine of that particular answer is, so this whole thing right here came out to be negative 0.99763, etc. And so putting those two results together, so I'm just going to multiply that by a factor of 3/2. I got negative 1.49644. So I'm just going to leave that as 1.496 watts. So looks like I had a smidge of rounding error when I solved it originally. But we got an answer that's close enough to for me to think I did everything correct here. So key caveats that I want to remind you of when you're doing these calculations later on today for this in-class assignment and also on your homework assignment. Phasors do not go into these instantaneous power relationships literally ever. We just take the parts of the phasors that we need, okay? And then the bigger one is omega t is always going to be an angle in radians because omega is always expressed in radians per second. So we need to convert that into degrees so that we can combine it with our phase angles, or transversely, if your calculator is in radian mode, leave omega t alone and convert your phase angle into radians so that your calculator is going to give you the right answer. Those are the two most common mistakes that I see in doing this calculation. It is literally just plug and chug. You just have to do it correctly. Okay. All right, so any questions about this before we move on to another pretty short topic? All right. So I'm going to circle back to my notes here, okay? So we used intuition, essentially, an understanding of how sinusoidal signals behave in order to determine our average power in our linear network here. I want to now take a more formal mathematical approach to how we would find average power in general, okay? And this is going to lead into some of the stuff that we're going to do in class on Friday. So let's say that x of t is a periodic signal with period capital T, right? This period capital T is simply the amount of time it takes for our signal to repeat itself, exactly how we defined it when we were looking at sinusoids specifically, but this definition right here could be true for any periodic signal. So you guys, I believe way back in Math 242, learned how to calculate the average value of any periodic signal, but I also understand that you may have forgotten that you learned that. So I'm going to give you that relationship here really quickly, okay? So if I have a periodic signal x of t, I can say that the average value of x of t, which I'm going to call x average, is going to be expressed as follows. So what we're going to do is we're going to take our signal, periodic signal x of t, and we are going to integrate it with respect to time. Okay. The bounds for this integral is that we are just going to integrate over exactly one period. So I'm going to choose to represent that as an integral from 0 to capital T, but we could just as easily say that it's negative capital T over 2 to positive capital T over 2, which you might see in some textbooks. It literally doesn't matter as long as we are integrating over exactly one period, okay? So I've got the area under the curve over one period. So what I'm going to do now is simply divide by the length of that period to give me the average value. And I'm going to choose to represent that by a multiplication by 1 over 2. So that is how I calculate the average value of a periodic signal. So let's apply this mathematical relationship to our instantaneous power, because we saw on all of those Desmos graphs that our instantaneous power is indeed a periodic signal, okay? So average power would be 1 over t times the integral from 0 to t of, in our most generic form, 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Close that guy off, dt. So what I'm going to do now to make the math a little bit easier is to compartmentalize things, or to break this into two separate integrals, okay? So I could break this guy up as 1 over t, open braces, times the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt plus the integral from 0 to capital T of 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. I want us to look at that second integral first. So we have broken this thing down into essentially our DC term, and we're integrating that DC term, and then we have the integral of our AC term. Well, our AC term in a sinusoidal system is a sinusoid itself, okay? So we are integrating a sinusoid over exactly one period, okay? So what is the area under the curve if we look at a sinusoid over one period? 0, because exactly half of the time it's positive and exactly half of the time it's negative, and the areas are going to cancel each other out. So this whole thing right here is literally just 0. So we would have 0 divided by our period, which is just going to be 0. Okay? And again, anytime we integrate a sinusoid over an integer number of periods, and I'm stating that because I'm going to use that relationship in class on Friday, the result of that is always just going to be 0. So realistically, our average power only depends on the DC portion of our signal, which is what we inferred when we were looking at the graphs and all of that kind of stuff. Well, all of that stuff right there is a constant, as we've already discussed. So I could move it completely out of the integral. And so I would wind up having 1/2 Vm Im cosine theta v minus theta I. That is going to be multiplied by a factor of 1 over t multiplied by the integral from 0 to t of dt. Well, the integral from 0 to capital T of dt is literally just capital T. So I have 1 over t times capital T. This bit right here literally just comes out to be 1. And so I'm left with an average power of 1/2 Vm Im cosine theta v minus theta I, which again is exactly what we just gleaned from looking at the damn graph to begin with, okay? So we've now got a more formal mathematical proof that our assumption about the average power is actually correct. And we'll use this as a jumping off point to determine what are called effective values for periodic signals at the beginning of class on Friday.